disabled. So my name is Jennifer, and I'm the park interpreter in Spruce Woods Provincial Park, which resides on Treaty 1 territory, home of the Anishinaabe, the Dakota, and the Métis Nation. Over the course of the webinar, if you have any questions, please type them in the Q&A box down below, and we will strive to answer as many questions as we can. So Manitoba Parks is committed to promoting a healthy dark sky by reducing light pollution and providing stargazing opportunities in provincial parks. Over this winter season, we are offering a series of webinars with our wonderful partners at Royal Astronomical Society of Canada. And today we are joined with Gord Tulloch, and forgive me, Gord, if I pronounced your last name incorrectly.
Perfect.
Oh, perfect. Awesome. We're here to discover how do we know that, which I'm very excited to learn. So Gord, I'm going to pass this over to you, and you're going to teach us all about how do we know that.
Well, thanks very much. And I figured since it's cold and it's kind of cloudy and it's not a really great time of year to go out and look at the stars, I figured we'd put a log on the fire, sit in our nice comfy armchair and do some armchair astronomy instead of what's up in the sky right now, which is what we usually talk about. So what I'll do is I'll share my screen here, and the host has disabled my screen sharing. So I'm going to just talk for a little while. So there we go. Perfect. Okay, so you should see my screen now, and what I'm going to talk about is something that springs into my mind whenever I hear somebody talking about astronomy and the universe and stars and things. And they say quite authoritatively, well, you know, this star weighs 4 solar masses and its diameter is this much, and it's got a companion that orbits it at a distance of this much. You always start to wonder, how do they know that? And why can they figure that stuff out when, you know, we can't actually touch these things? So what's the deal? So as you can see, I'm a member of the Royal Astronomical Society. I run a small observatory in my backyard, and I also belong to an organization called the Association of Variable Star Observers, and they've given me a designation, TGR, which I just call it Tiger. And as a member of the Royal Astronomical Society of Winnipeg Center, it's obligatory that there must be a cat in at least one of my slides. So there's my cat. So, okay, so we can tick that box off. I can move on. So, excuse me. So how do we touch a star? First of all, they're pretty far away. We have a star that's fairly close to us, which is the one in the picture, our sun. But even so, it's kind of hard to get there, and it's kind of not fun once you're there because it's hot and it's dangerous. There's radiation, all that kind of stuff. So how do we figure out things about things we can't touch? And one way we've done that, of course, is we've sent robots, and we've sent a lot of different robots to a lot of different places. This one is the Galileo robot that we sent to Jupiter, and it looked at Jupiter and its moons and took some great pictures and eventually crashed into the atmosphere, and we learned a lot about it. But, you know, as distances go, our solar system is actually very close to us. There's you know, a lot of space within our solar system, but at least we have a scale of a few years to get to various parts of the solar system. Whereas if you look at the star probes that we've sent out, the Voyager probes that we sent out in the 70s, they have just barely crossed the threshold of the edge of our solar system on the way out to interstellar space. And they've been journeying for, you know, 50 years or 40 odd years. So it takes a long time to get anywhere in space. So we can't really send robots to look at other stars because they're just too far away. And once they get there, as I said, it's too hot, it's too dangerous. So what do we do? Well, the good news is we've learned how to tell a lot of stuff about the stars and galaxies in our universe simply by analyzing the light that we get from all of these stars. And that's what this presentation is about, all the different ways that we've figured stuff out. And it's actually surprising that we've known about this stuff for quite a long time. Like, we're not making this stuff up, or I should say, we're not making this stuff up, but we're not figuring this stuff out just recently. We've known about this stuff for hundreds of years in a lot of cases. So we'll talk about what we've figured out and how we've learned it. We'll talk about things like how hot is something, what's it made of, how far away it is, how big and heavy it might be, and what might be orbiting it. So, and we can figure this stuff out based on the light that comes from these objects. But we need to learn a little bit of basic physics first. So don't worry, this won't hurt. But we're going to go back to the 1700s and Isaac Newton. Now, Isaac was a smart guy, and he figured out a lot of stuff about a lot of things. If you look at a lot of different disciplines within science, you'll find that Isaac Newton advanced those disciplines single-handedly in a lot of cases, a long way. In some cases, he worked with other people. Sometimes he worked against other people, but Isaac really advanced a lot of disciplines, and we're going to talk about two of those things tonight. So first of all, Sir Isaac Newton, he learned a lot about optics and learned a lot about light. And one of the things he learned about light was if you take white light and you shine it through a piece of glass called a prism, and you can see the prism in this diagram, that it's just a triangular piece of glass. But if you shine white light through a prism, the different colors of that light pass through the prism at slightly different angles. And what it does is it causes the colors that are contained within that light to spread out so that you can see something called a spectrum. And the big breakthrough that Isaac Newton managed to achieve was that he discovered that light is composed of many colors. And what we've learned subsequently is that the colors of light correspond, just like in sound, it corresponds to frequencies of light. So a certain color of light will correspond to a certain frequency. Just like on sound, if you've got a certain frequency of sound, the pitch of that sound is a different frequency and vibrates at a different frequency. So this splitting of light enabled a lot of ways that we can actually analyze starlight to see what things are made of and how they work. So we're going to go through a few of those. And of course, you've seen a lot of these spectrums in your own life, because just like a prism can split light into its component colors, so can things like raindrops, right? They refract that light and it creates things like rainbows. And you'll see the colors in a rainbow are the colors of a spectrum. It starts at red and goes all the way through purple and or blue and purple and violet, right? So you're very familiar with spectra just in your day-to-day life. And if you take a garden hose and on a sunny day and you spray it on your lawn, you'll probably see spectra refracted in the droplets that are hitting your lawn. So basically, if we look at these spectrums, there's some things that we've been able to learn in the laboratory which are very helpful in analyzing these spectrums. First of all, we've learned that most objects, and they can be like a bar of iron or they can be as something like a star, they give off a radiation in a continuous spectrum, and it's called a black body because it's a perfect radiator. It starts off black, and as it gets hotter and hotter and hotter, you can see different colors come out. And a bar of iron is a good example. If you heat up a bar of iron, it eventually starts turning red, and then it gets hotter and hotter until it gets blue hot and white hot. In some cases, you don't see specific colors because all of the colors are kind of blending together, and you see things turn white because it contains all of the other colors as well. So if you look at a light bulb, for example, and it may have a tungsten filament in it, that's a black body, and that radiates if in a continuous spectrum, so you see all the colors of the spectrum. But what's interesting, if you take a gas like neon, for example, in neon lights, a hot gas actually won't give you a continuous spectrum. It gives what's called an emission spectrum. So only certain frequencies or wavelengths, as we call them, I'll probably use those two things interchangeably. Each of these different frequencies are what's emitted by this hot gas. So the fact that we can actually look at these gases in the laboratory, we can heat them up and we can see what they look like when they're emitting light, means that we can look at stuff far away. And if it's emitting the same spectrum, we have a good idea that, yes, that's the same material. And this is how we've figured out what things are made of, because we can look at their emission spectrum, and the light they're emitting tells us exactly what they're made of. Similarly, if we have a cold gas and it's in between us and the source that's emitting, so we've got a black body that's emitting a certain continuous spectrum, but we put a cold gas in between, then we'll see that gas is actually absorbing some of the radiation, and that will turn into little black lines in our spectrum. So we could be looking at emission spectrums where we have bright lines, or we could be looking at absorption spectrums where we have dark lines. And you'll see examples of that as we go through our presentation. Excuse me. So I'm just going to see if I can bring the chat up in case there's any questions that might come up. Any questions so far?
No questions yet, but when I see any, I will make sure to let you know and I'll read them out for you.
Okay, perfect. Feel free to break in at any time.
Okay.
So here we have a spectrum, and this is a spectrum of a star, and we notice that there's definitely absorption lines in this spectrum, and we know that certain colors correspond to certain frequencies. And these days, because everything's metric, we measure these spectrums and these wavelengths and frequencies in something called nanometers, which is 1/1,000,000th of a millimeter. So it's a very, very small measurement. So the frequencies of visual light is actually very, very fast. The visible light frequencies and wavelengths are very small. So, but by looking at these spectrums, we can see a number of things that we'll talk about. First of all, we'll notice that there are parts of the spectrum that are brighter than others. And we've learned that that actually can tell us a lot about the temperature of what we're looking at. We also can see bright lines and dark lines, of course, and that's the emission and the absorption lines in the spectrum. And that will tell us a lot about the chemical signature of the material that we're looking at. As well, some parts will be brighter than others in other ways, and that can tell us about the physical conditions under which we're looking. And finally, line positions can vary from place to place. So if we're expecting to see, for example, you'll see the hydrogen beta line at 500 nanometers, and then all of a sudden it's displaced from that, we know that there's some sort of speed involved, and we'll talk about that as well. One thing I should point out as well is the visible spectrum is actually a very small part of the overall electromagnetic spectrum, and we call it all radiation. This is all radiation. I know radiation is kind of a bad word, but in science, radiation just means there's something being radiated, right? So we can see in very short wavelengths like AM radio, or I should say very long wavelengths, for like 10 to the fourth meters. So that's 100,000 meters. We see AM radio, very long wavelengths, and shortwave radio, TV transmissions, microwaves, right? And we see these wavelengths getting shorter and shorter as we go through radar. And then infrared, we feel as heat. So infrared radiation, we feel as heat. And then we see the visual spectrum, right? They're all going from red all the way through to violet. And then once we pass the visual spectrum, we get into what's called ionizing radiation. And then this is the bad stuff, right? So if you're out in the sun and you're getting hit by ultraviolet light, that's ionizing radiation. And what ionizing radiation can do, if it hits the atoms and cells in your body, it can break them and cause all sorts of bad things to happen. So ionizing radiation is bad. Non-ionizing radiation, like all from infrared all the way back, or actually from visible light all the way back, that's not dangerous simply because it's not ionizing radiation. Now, that doesn't mean you can go to the top of the radio tower for one of the radio stations that broadcasts at 100,000 watts, stand beside it and be unharmed, because the intensity of the radiation has something to do with that as well. So if you're standing on the top of that tower, you're gonna not be in a good place, because it's very, very intense. Even though it's not ionizing radiation, it's very intense radiation. And that's what's funny about when people are talking about things like Wi-Fi being a problem. Wi-Fi uses actually microwaves, which are sort of in the low end of the spectral range at very, very low energy. So the amount of interaction that you have with the Wi-Fi devices is very similar to the kind of interaction you have with FM radio. So nobody worries about having an FM radio in their house. So nobody should worry about having Wi-Fi in their house either. So it's all radiation, but some radiation is quite harmless. So, for example, we would like to figure out how hot something is. So this is an experiment with a little bit of equipment, and I'll show you the equipment I have, but with a little bit of equipment, you can do this experiment yourself. And what I've got in my backyard, I've got an observatory that's just basically a shed. And the shed roof rolls back and it reveals my telescope, and I can use my telescope in the backyard. You can tell it's my backyard because I've got my neighbors next door with his annoying Christmas lights. And it's right in the middle of a suburban neighborhood. Excuse me. So what I can do with my telescope is I can put a little filter in my telescope that acts the same as a prism. It's actually a dispersion grating, it's called, but it's the same sort of thing. You can see the spectrum on the surface of the filter. Now, this little star analyzer, as it's called, what it does is it spreads out the light from a star. So if I point it at a star and take a picture, I get something that looks like this, where I've got the actual star. I'll get my laser pointer out here. I don't seem to have a laser pointer. Okay. You see the star, and then you see a spectrum of that star, and then you see some echoes of that reflection. So what we can do is we can cut out this spectrum, and then we can analyze it. And what we've discovered, and this compares to what we've discovered in the laboratory, that if we make a graph of the wavelength compared to the brightness, we discover that if a star is not very hot, its peak intensity is radiating in the red. So that's a red star. It's not very hot. It's only 4,000 Kelvin. Kelvin is kind of like Celsius, except it starts at minus 273 Celsius, which is absolute zero. So when you look at Kelvin, you take subtract 273, and that turns it into Celsius. So at 4,000 Kelvin, a star that radiates mostly in the red is quite cool. So we can figure out, okay, that's radiating at a certain wavelength in the red, it's quite a cool star. But if we see that the star is radiating more in the green and yellow, like our sun, this is approximately our sun's temperature, 5,700 Kelvin, we can see the peak intensity is in the yellow-green area, and that tells us that temperature. And finally, if we see that a star is radiating primarily in the violet or the ultraviolet or even higher levels, that tells us a lot about how high that temperature is. So this particular star, if we saw the peak intensity at 7,500, in the purple and the violet, we can see that would be about 7,500 Kelvin. The reason we can put numbers to this is a guy by the name of Wiens created this law where he was able to say, okay, the peak the peak intensity of this light in centimeters, so you have to multiply it out properly, is a simple relation 0.29 divided by the temperature. So if you want the temperature, you do a little bit of algebra and you say that the temperature is the peak intensity divided by 0.29. And now we can tell what the temperature is if we know what the peak intensity is. If we take a spectrum, we put it on a graph, we now know what the temperature is. And that works for lots of different stars. And what we've done is for each of these stars, we've calculated that and put them into classes. And we'll talk about that in a sec. Now, what we can also do is we can also find out what it's made of. And once again, we're looking at a spectrum. This one's in black and white because we don't necessarily need the colors. And if we graph that out, we'll see that there's emission lines in this spectrum, and there's also absorption lines. So with stuff that sticks up from the baseline is an emission line, and the stuff that is lower than the line is an absorption line. So, and this is just in the yellow to red, but we know that if we see these lines at certain parts of the spectrum, at certain frequencies, we know the element that actually causes these things to have these colors. So we look in a book and we see that helium absorbs light at 6,777 angstroms. An angstrom is 1/10 of a nanometer. That's an old way of measuring it. And we know that if a star is emitting at 65, 63 angstroms, we know that this is a hydrogen. So basically this star, if it's an emission line, we know that it's emitting light in hydrogen. So we know that star is made out of hydrogen. But if it's got an absorption line, we also know that that star is surrounded by a cloud of helium that's absorbing some of its light. So we can know a lot about what a star is made out of just by looking at these lines on spectrums. And combined with the temperature, this has allowed us to create different classes of stars. And these classes are easy to remember if you're an astronomer because we've made a bit of a mnemonic about this. This is "Oh, be a fine girl, kiss me." So astronomers are ever hopeful and don't get out much. But this mnemonic allows us to remember what these spectral classes in, with the coolest red stars being in the M and the hottest white stars being in the O's. So if we look at the spectra for each of these stars, we can see that certain classes of stars, like the A class, and that's a star like Vega, which is a bright star you see in the summertime, we can see that there are certain spectral lines in Vega's spectra which denote hydrogen, and we know that A stars are predominantly hydrogen, so we see a lot of hydrogen. Whereas if we look at stars that are M class, like 61 Hercules, which is a star in Hercules, we see that they have much more complex spectra with other elements in them, like titanium oxide and silicon and nitrogen and carbon. And these are stars that have what are called metals in them, and they're older stars, and they've probably been seeded by supernovas, which have created all of these different elements in them. So we can tell the chemical composition of these stars as well as its temperature just from its spectrum. So I'm just going to take a pause here. Hopefully that was clear to everybody. Are there any questions? Now's the time.
Nothing at this time yet.
Okay, then we'll just carry forward. So now we know what things are made of, and we know how hot they are. What about if they're moving? And this is really important for a lot of different purposes. But the thing that we need to think about is when you're sitting at a train crossing and a train's going by, there's a very characteristic sound that you hear. It's a high-pitched sound followed by a low-pitched sound, and I'm going to try to duplicate it for you. It's when the train goes by, it goes meow, right? And what's happening there is the sound waves in front of the train is actually being compressed, and the sound waves behind the train are being uncompressed, right? And this is something that Christian Andreas Doppler discovered. He published a paper in 1841. And what he figured out is something we now call the Doppler effect after him. Sound and light waves compress in the direction of movement of an object. In light, it means that if the object is approaching, we see it as bluer, and if it's retreating, we'll see it as redder. So just like the Doppler effect, where we've got a car that might be traveling down the road, just wait for my little animation to decide to load. Maybe it's not going to. Just being fussy today. Okay, so it's a little car. If we look at the plane in the picture here, you'll see as the plane is pushing forward, it's compressing all of these sound waves, and that is raising the frequency of the sound waves so that they're coming more often. Similarly, if we look behind the little airplane, we see that these sound waves are being less compressed, which means they're reducing in frequency, and we get that characteristic sound. So if we look at it from a light point of view, we'll see the middle bar here, the middle spectra, we'll see that the absorption lines on the spectra are at the frequencies where we expect them to be based on what we've done in the laboratory. We've passed light through cold gas, and we've observed that certain elements create these absorption lines. But if we see a spectrum of a star and it's actually got these lines shifted towards the blue end of the spectrum, we can tell that this star is moving towards us. If it's shifted toward the red end of the spectrum, we can tell that these stars are moving away from us. Very easy. So if we look at things now like binary stars, this is a beautiful binary star in Cygnus called Alberio. If we look at these stars that have companions, in some cases you can see them visually, like this one. But in some cases, you aren't actually able to see the companion star that's orbiting the main star. So most stars in our galaxy are binary stars, but not all of them are actually visible binaries. Sometimes if you want to tell whether a star is binary or not, you need to look at its spectrum and look at it. And these are called spectroscopic binaries. What's really interesting about binary stars is they give us a wealth of information based on the light that we get from them. And we'll talk about binary stars for a little bit. So if we look at a spectroscopic binary like this 57 Cygni, which is a star in Cygnus, we can see that there's a spectrum. This is an absorption line here, and this is an absorption line here, and this is the frequencies, which don't really matter. But if we take pictures of this star or spectra of these stars over a period of time, what we're going to see is there's going to be shifts in that spectrum. And if we measure those shifts, we can see that that shift, as that companion star works its way around the other star, we're going to see a red shift when it's going away from us and a blue shift when it's coming towards us. And we'll see the whole entire spectrum of the star actually undergo these shifts. And that makes it easy for us to tell that this is in fact a binary star. Now, binary stars are interesting because we can actually tell a lot about them in other ways. For example, if we wanted to know how big these stars are, it's kind of hard to go and weigh a star. It's, far away and hot and dangerous and all that kind of stuff. But we actually know how big things are, and we can infer the size and mass of these stars, as we call it, by the way they interact together. And what we notice with these stars, and this is, we can visually tell this in some stars like these pictures here, that stars orbit each other with a certain period. So they start orbiting, and it may take a year or two for them to complete an entire orbit. And if we want, we can take pictures, and based on the pictures, we can tell how long it takes for them to orbit, right? And what we can also tell is the stars are actually of different masses. And based on that, they'll orbit around the center of mass. They won't orbit, the little star won't orbit around the big star. It'll orbit around the center of mass. So what we'll see is the ratio between the mass of the big star and the mass of the little star based on where this center of mass is. If these two things were the same mass, then the center of mass would be in the middle of this teeter-totter here, whereas this high mass star and this is a low mass star. So the center of mass works towards the high mass star. Now, this animation isn't working either, apparently. But what this animation was is you could see that the center of mass is actually within the mass of the large star, and the small star orbiting around it would allow that large mass to actually make not a circle, but it would actually revolve around this as the small mass was revolving around it. So because we can see either spectroscopically based on the red shifts and the blue shifts what the rotation period of these stars are, we can make use of something that a guy called Johannes Kepler discovered in 1609. Remember, I said that we've known about a lot of this stuff for a long time. Johannes Kepler was a very religious guy. He was a German fellow, and he lived in Germany, and he was a astrologer to some of the bigwigs in Germany, and he was hired to cast horoscopes and things. But what he also wanted to do, because he was a very devout fellow, is he wanted to discover how the heavens worked. And his idea of the heavens was they must work in perfect circles, and they must follow paths that are geometrically perfect, because of course the heavens should be perfect. So Johannes Kepler spent years trying to figure this stuff out. And finally, he fell in with a guy by the name of Tycho Brahe. Now, Tycho Brahe was a lot less devout. He was a bit of a party animal. He had a nose that was made out of gold because somebody had cut off his nose in a duel earlier. And he lived a life of excess. As a matter of fact, most people think when he passed away, it was because he got a bladder infection by not wanting to leave the table during a party when he felt the call of nature. So it eventually did him in. But what Tycho Brahe was a master of was determining the exact positions of things in the sky. And working with Johannes Kepler, who was a mathematician and a theoretician, he was able to take the precise positions that Tycho Brahe created and determine that, in fact, the heavens didn't work in perfect circles. And a matter of fact, he created some planetary laws, which are really critically important to us when looking at not only the orbits of planets, but the orbits of stars. And the first law he discovered is planets don't travel in circles, they travel in squashed circles, kind of egg shapes, called ellipses. Second law is that planets sweep out equal areas in equal times. I'll show you a picture of that. That's a little harder to understand. And then finally, the one that's important to us is he discovered that the orbital period of a star is equal to how far away it is from the other star. Okay, never mind about the squares and the cubes and that kind of mathy stuff. But that was the really critical thing that he discovered, because that allows us to basically say, if we have the orbital period of a star around another star, we also know what the distance between those things are. Now, if you look at this graphically, you can see this is an ellipse. This is kind of a squashed circle. And the big thing is at one of the focuses of this circle. And as a star goes around, it travels slower when it's further away. So the area that it sweeps out is smaller. And as it gets closer to the star, it goes around quickly. And that's really helpful in explaining what we observe on different planets, particularly in our solar system, which is mostly what he was concerned with. So all of a sudden, Kepler has given us an important piece of information, but it actually remained to our good old friend Sir Isaac Newton to really explain what the heck was going on there. So Isaac Newton was brilliant for optics, and as you can see, he actually created the first reflecting telescope. Up to that point, telescopes were made out of lenses instead of mirrors, and just like a prism, lenses had a tendency to make light split up. So when you're looking at a object through a telescope made out of lenses, you see false color, and you still see that today. If you go to the department store and you pick up a cheap refracting telescope, they're called, the one that uses lenses instead of mirrors, and you look at a bright object, you're going to see a purple fringe around it because it's actually, the light is actually splitting out and not focusing it in the same place. So this issue was something that Newton wanted to fix, but he fixed it by creating the first reflecting telescope, which doesn't have false color because it doesn't use lenses. But one of the other things that Newton did is one day, you can see the apple tree behind him. One day he was sitting under the apple tree contemplating the universe. The fact that an apple may have fallen on his head, nobody really knows if that's true. But what he was looking at is the moon, and he watched the apples fall and he looked at the moon and he realized that everything in the universe works from the same kind of model, and that the uh, universal law of gravitation is that bodies attract each other based on their mass, based on how much they weigh. If you have a very large object, then it'll have a great attraction, like the Earth on the moon. If you have a very small object, like an apple, it will not have a very great attraction. It'll be mostly attracted by large things like the Earth. And by creating the law of universal gravitation, Newton finally solved the puzzle of how we can tell how much things weigh, because if we can see how far apart they are and how they orbit each other, we can use the law of gravitation to calculate their overall masses for the entire system. So if we add the masses of the big star and the little star, then we can tell the exact mass of the entire system. But because we know the radius of their orbit and the sum of their masses and the ratio of their masses, we can actually say what each of them weighs. So with nothing more than the light they produce, we can weigh a star.
I do have a question, Gord.
Sure.
It is back about emission and absorption. So they were asking, how do we observe emission and absorption spectrum? And by that, they mean, what device do we use?
So again, I won't go back to the slide, but you saw the little filter I use on my telescope called the star analyzer. That will show you both. Okay, so and I actually have, if this was an in-person demonstration, which unfortunately we can't do right now, I have a little device that is also a diffraction grating that you can point at different things in the room. So if you point at a incandescent light, which has a, uh, glowing filament in it, you're going to see a continuous spectrum. But if you point it at an LED, which only emits on one frequency, or a neon tube, which only emits on one frequency, you will see those emission spectrums. So another way to see an emission spectrum, or really to get a diffraction grating on the cheap, is actually use the surface of a CD. If you look at the surface of a CD, the other side without the label, obviously, and you hold it up to the light, you'll actually see on incandescent, you'll see continuous spectra, and you'll see emission spectra, depending on the type of light you're looking at. Now, the resolution of that isn't very good, so you're not going to see absorption lines in that, but you will see absorption lines in tools like the star analyzer that I use, because it has a fine enough ruling on it that you can actually see the absorption lines. And if you put it on a graph, you can see that there's dips and peaks based on where those are. So it doesn't take a lot of tools to actually do it. What I did for my telescope, instead of going out and spending $200 buying a star analyzer from the company that makes them, I actually bought a $5 diffraction grating from AliExpress, and it came from China. They cost about $5 each. I put it in a little filter container, and I use that for my telescope. So it doesn't take much to get a diffraction grating. And once you've got a diffraction grating, you can look at the stars and be able to see absorption lines in their continuous spectra. Emission lines are a little harder in stars because they are black bodies and they emit light in a continuous spectrum. So if you wanted to see emission lines, you're looking for things like neon and LEDs and things like that that only emit on one frequency. So I hope that answers that question.
Excellent. Thank you.
Cool. So we know what stars are made out of, and we know what they weigh, and we know that they move based on the shifting of their spectrums. Now we want to find out, well, do stars have planets around them? And if so, how are they, are the planets affecting the stars? So one thing we could do is by direct observation, we can see some planets around other stars, and these are called exoplanets. So I'll use that term. So if you see in these pictures, we've got pictures of stars, and if they have really, really large planets, if we put a little screen in front of the image of the star in our telescope, we can see the planets. Even though they're much, much, much dimmer than the star, we can actually take pictures of the planets around the star. And what you see in the first picture are 3 different planets around this star. And then in the second picture, you'll see there's a bit of a disk around this star where there's planets forming. So most of the time, we're not able to see planets directly. So we have to look at the light from the star and infer that there are planets. Oh, good. And this one is actually working. This is the same animation that I had earlier in the presentation that didn't work. But again, remember when stars and planets and stars and things are orbiting around each other, they're orbiting around a common center of gravity. Like you don't see the little thing orbiting in a circle around the big thing and the big thing moving. They orbit around a common center of gravity. And if the object is big enough, like a Jupiter size planet or bigger, and we are looking at these planets from sort of a top down view, like we are with this one, what we're going to see is a wobble in the planet. I should say in the star. And we have instruments that are fine enough now that we can actually detect these wobbles in stars that are relatively close to us. And if a star is wobbling, it has a big planet near it. So we can infer not only the fact that there's a planet there, but also the mass of that planet, because we know how to calculate masses between big things and small things that are in orbit around each other, right? We just went through that. So now we can tell whether there's planets around other stars, but only if we're looking at them kind of from the top down. If we're not looking at them from the top down, there's another way we can tell that there's a planet. Once again, we're using the Doppler shift of spectrum of the star to tell whether or not there's a planet going around it. Because what'll happen if there's a planet going around a star, if the planet is coming towards us, we'll see a little bit of a blue shift in the spectrum of that star. If the planet is going away from us, we're going to see a little bit of a red shift in the spectrum of that star. So if we see the same kind of oscillations in the spectrum that we see with binary stars, we're going to be able to see that there's a planet involved. And then once again, because of the amount of the shifting that happens, we can also infer what the mass of the planet is and all sorts of things, right? Now, we've found a ton of planets. There's thousands now of exoplanets around other stars that have been detected. Initially, we didn't have a lot of stars detected because we were only able to detect very large planets that caused a big wobble or a big shift in the spectrum. Now we have finer and finer sensitivity instruments, and we can now detect Earth-sized planets going around these stars. And we've detected a bunch of Earth-sized planets around these stars. So there's one other method that we can use as well. And once
One
again,
second, Gord, I do have one more question.
sure,
from
go ahead.
someone here. This is from Emily. She says, I understand how we can get the relative masses of the bodies in the system, but how do we get the actual number rather than just the ratios?
Well, because the radius of the orbit, we can tell. If you're familiar with universal gravitation, and I'm not going to talk about math, but if you do a Google search for universal gravitation, you'll notice that there's a few different terms in that equation. One of the terms is the radius of the orbit. So if we know what the radius of the orbit is, and we know what the masses are, and we know what the sorry, we don't know what the masses are. If we know what all of the masses turn out to be based on the orbit, we can then use the ratio between those two things to calculate the mass of each individual part. Remember what I said is that if you put the big star and the little star on a teeter-totter, they're going around a certain center of gravity. So that is the radius of their orbit. So if you Google detecting the mass of a star, you're going to see the actual equations involved. It's university level math, but it's not terrible stuff, right?
Thanks.
But all you're doing is you're figuring out the numbers that you need to plug into these magic equations to get a result. So once we've had Kepler and Newton both working on this stuff, we were able to plug these numbers in and solve for the mass of the planet. So
there's another question here
sure.
from another individual. It says, in the case of a solar system, does the center of mass include all the planets versus the sun? So if there's more than one planet, can it still make the same wobble as one planet?
Yeah, and obviously the motion becomes complicated. It's usually not as complicated as it could be because you don't usually have more than one Jupiter. Sometimes you do, and sometimes those planets are kind of on the same side of the sun and the wobble will be pronounced. Sometimes those planets are on different sides and the wobble won't be there at all, right? So it's a complicated motion. It's not terribly simple when you start talking about multiple planets, and that makes it harder to detect planets that might be smaller, or there may be multiple large planets. So we have many, many more planets to discover. Sometimes they're not conveniently located for us, and sometimes there's more than one of them, and that complicates the whole thing. But it's a really interesting thing to actually observe exoplanets with your home telescope. And there's actually a course that the American Association of Variable Star Observers actually has a course that you can take to learn how to observe exoplanets. And in particular, this next thing we're going to look at, you can watch an exoplanet pass in front of its star just by detecting how bright it is. So hopefully that helps. So what we could talk about now is another way of detecting whether or not there's a planet around a star. And one thing we do a lot with variable stars, which we'll talk about later, these are stars that get brighter and dimmer and brighter and dimmer on a fixed pattern, is we can detect how bright they are to very, very high resolution, even in backyard telescopes like mine. So when you analyze the brightness of a star and you see that it is undergoing a change, then there can be a lot of different mechanisms for that. Sometimes those are intrinsic in the star itself, and we'll look at that a little bit later. And sometimes it's because there's something else happening. So when we want to look at stars and determine whether or not there's a planet happening there, if we happen to be looking at the star system edge on, not from the top before where we'll see a wobble, but if we're looking at the system relatively edge on, we can see the planets around that star passing in front of it. And what happens is, you can see this graph here, the brightness will start to diminish as soon as we start to see that planet passing in front of the star. It gets dimmer and dimmer until once that planet is starting to leave, you'll see the star appear to get brighter again. And that's based on the size of the planet as well. If the planet is not very big, it's very difficult to detect because the change in the brightness, excuse me, is very low. But if this is a big planet, you're going to see a fairly dramatic change in the brightness of the star. And what we've discovered is that that's a really good way to find exoplanets. And for amateur scientists like me, it's actually a way of detecting exoplanets that I can directly observe, because if one of the satellites that are up in orbit that are doing this for thousands of stars at a time have discovered an exoplanet orbiting around a star, we now know that it's there, so we can look at that star and figure out when it's going to start dimming, and we can actually observe that event with our backyard telescopes. And we take a whole bunch of pictures of it, we figure out how bright the star is, and we can create a graph similar to this one and find out stuff about that exoplanet. So it's very interesting. And as I said, there's a course at the Air Association of Variable Star Observers on doing just that, if you're interested. You don't need super expensive equipment. You just need a backyard telescope and a camera. And you can
Gord, one person was
observe this
wondering
stuff.
if you wouldn't, pardon me, sorry, he was wondering if you wouldn't mind letting us know what type of telescope you have exactly.
I have a Celestron 8-inch telescope. It's on a robotic mount, Orion Sirius mount. Not super expensive, you know. It's an 8-inch telescope like that, brand new, will cost you a couple of $1,000, and you can probably get it used for under $1,000. So it's not a super duper telescope by any stretch of the imagination. But this telescope is completely automated. It's you know, it's got automated focusers and all that kind of stuff. So I can sit in my house and operate the telescope without sitting out in the cold or sitting out in the mosquitoes or what have you. So Celestron 8-inch telescope is a great tool to do science. Even smaller telescopes are fine, but you probably want to talk to your friends at the Royal Astronomical Society before you buy a telescope, because there are some telescopes that are definitely not suited to do this kind of work. But yeah, you can do all sorts of science, particularly in spectroscopy, which is when we're looking at these spectrums, as well as photometry, as it's called, which is analyzing the brightness of stars, which is exactly what we're doing here. So photometry, you take pictures of stars, and based on the intensities of the other stars, you can estimate the intensity of the star you're interested in. And we'll look at that in a few minutes with variable stars, because they've become a very critical part of figuring things out about our universe as well. Is there any other questions?
Yeah, there's one last one here which asks, how do stars take shape?
So they're spheres. So that's probably not what you're asking. Stars form from gas clouds in the sky, and if you're an astronomer, you've probably taken pictures of a lot of these gas clouds. And if you're interested, you can look at a picture of a giant star forming region in Orion called the Great Orion Nebula, M42. And what happens in these star forming regions is something disturbs the gas cloud. Maybe a star goes by or whatever, and it causes it to start rotating. And as it rotates, it compresses, and the area in the middle starts compressing, and it sucks up more of the gas until it gets to a certain size, and then it ignites and becomes what's called a protostar. And these protostars continue to collect gas, and finally they turn into full blown stars, and then they carry on with their life cycle. Sometimes stars don't have a lot of mass because they didn't have a lot of gas in that cloud, and they're very long lived because it takes them a long time to get hot enough to burn up their fuel. Whereas if a star has a lot of fuel and becomes very, very large, massive or supermassive as we call them, they can have very short lives from a cosmic sense, only billions of years instead of tens of billions of years, and they can blow up and do other cool things. So that's an entire separate lecture on stuff like that. Any other questions?
That's it for now. Thank you.
Good. Okay, so now we can detect planets around other stars just using the light that we get. We can either watch for wobbles, we can look at spectra and see red shifts and blue shifts and that kind of good stuff, or we can use photometry and we can analyze the brightness of the star to see whether or not there's a dip in the brightness, and that kind of tells us, based on the amount of the dip, how big the planet is. So there's actually satellites in orbit that watch a bunch of different stars all at once, and they are there specifically to detect exoplanets using the brightness changes within the stars. So they're pretty cool. So the last thing I wanted to talk about, and I know I'm running out of time and I've got to talk fast because I've only got 4 minutes. Can we run a little long, Jennifer?
Yeah, I'm sure a few minutes later is not going to be a problem.
Okay, I was going to say I'll take that as a no, but okay, good. So quickly, I just wanted to talk about, how do we know how far away things are? Because that's kind of hard as well. You can't go out and measure with a measuring stick because these things are extremely far away, right? As a matter of fact, the closest star to us is a star called Proxima Centauri. It's 4.2 light years away, I think. Now, a light year means that's the distance a light travels over time. And if light is traveling at the speed of light, it's traveling at 300,000 kilometers a second. Okay, so that's a little further than the distance between the Earth and the Moon, which is 240,000 kilometers, I believe. And so it would take just under a minute for that light to get from Earth to the Moon, which is a fairly significant distance, and it's going extremely fast. It would take about 8 minutes for the light from the sun to get to the Earth, traveling at the speed of light, but it would take 4.2 years for the light from Proxima Centauri to get to the Earth. And that is the closest star that we can see in the night sky. So these distances are immense. So getting out and measuring them by hand is utterly impossible. So we have to use, once again, the light from these stars to figure out how far away they are. And we've discovered over time, there's a few different ways to discover these things. Sylvia raised her hand. I'll let her answer her question. I'll carry on. So one way to do this is something called parallax. And if you hold your finger in front of your eye, in front of your face, okay, I'll actually look at the camera. Sorry, my camera is off to the side. So if you hold your finger up in front of your face, and then you close one eye, and then you close the other eye, close one eye, you'll notice your finger moves, right? Because the angle at which one eye is looking at your finger is different than the angle at which your other eye is looking at your finger. So your finger kind of jumps back and forth, right? Well, it works the same way, except the Earth is traveling around the sun. And because the Earth is traveling around the sun, when it's on one side of the sun, say in August, we're looking at a star from a bit of an angle. And then if we look at the star again in February, right, half a year later, we're over on the other side of the sun. So we've gone 93,000 kilometers or 93,000 miles and 93,000 miles. So we're a long way on the other side. For stars that are very close to us, we actually can see that shift, except it's really, really small. Right. For many, many years, they thought this method was not working for them because they just couldn't see any shifts. It wasn't until I think the late 1800s that we got measuring devices that were precise enough to actually be able to measure this. The measurement for Proxima Centauri, for example, is 1 arc second. right? Now, an arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. The moon is about 30 arc minutes wide. So what we're talking about for 1 arc second is about 1/1800th of the size of the moon, the apparent size of the moon in the sky. So it's really small. It's a really small quantity. So you need very precise measuring tools. We have those tools now. So we've used parallax to actually detect the distance to a lot of different close objects. But once the objects are far enough away, parallax doesn't work because the quantity is too small. The way it shifts is too small. So we need to use another method. And one very, very important discovery that was made around the 1920s was that there are variable stars in the sky, and variable stars are basically stars that vary in brightness, right? Sometimes, like this one, they get bigger and smaller and bigger and smaller. Sometimes they have dust that passes in front of them and makes them dim. Sometimes they have other stars that pass in front of them and change their light, or even exoplanets. So variable stars, there's lots of different types of variable stars, but one very specific type of variable star was discovered in the 20s by this lady, Henrietta Leavitt. And Henrietta was a computer. Her job at the Harvard Observatory was to make calculations, because they didn't have real computers. They didn't have digital computers back then. So they hired people and they called them computers. And these computers would do things like tally up rows of numbers or look at photographic plates and see what was happening on those plates. So Henrietta was a very good computer, and she discovered something very interesting about a certain type of variable stars. The variable star, we call them Cepheid variables now, because the prototype for them is a star called Delta Cepheus in the constellation of Cepheus. But Cepheid variables have a one very interesting property, is that the variation of their light, the period of the variation of their light, is proportional to their absolute brightness. In other words, their actual brightness. When we look at stars, we see them from far away, so their brightness diminishes over distance, right? But if you were at a certain set distance from a star, looking at it, it would be of a certain brightness. The period of a Cepheid corresponds to the actual brightness of the star. Because we know how much a star dims when we go far away from it, all of a sudden we can tell how far away a Cepheid variable is, because we know what it looks like if you're up close, and we know what it looks like from far away. So we know the absolute magnitude, as it's called, and we know the apparent magnitude. And the difference between those two things is a function of distance. So all of a sudden we can look at Cepheid variables in our galaxy, and we can tell how far away they are. So Henrietta Leavitt doesn't get enough credit for this. Henrietta didn't get a Nobel Prize. Her boss did, if you can believe that. So Henrietta gets a mention every time. And there's actually a play about Henrietta that my wife and I saw when we were down in New Mexico a few years ago. If you ever have a chance to see that play, which the name is escaping me, it's an excellent play. And all power to Henrietta, because she was a real game changer. So what happened once Henrietta had discovered this, other scientists, notably a guy called Edwin Hubble. And now Edwin was a bit of a character. He went to Britain for a few years. He was an American. He went to Britain for a few years, came back with a British accent and a pipe that he would smoke. He affected being British from then on. So he was an odd guy, but he was brilliant. And what he discovered, looking at other galaxies and looking at a picture of the great galaxy in Andromeda, he discovered Cepheid variables in Andromeda. That means that if you can see a Cepheid variable, you can see how bright it appears to be, and based on its period, you know how bright it actually is, and you can tell the distance to that object. So that gives us a yardstick that we never had before. And we could tell that that galaxy was 275 million light years away. And that had big connotations to our understanding of the universe, because previously people had thought galaxies like the Andromeda galaxy were part of our own galaxy, just gas clouds in our galaxy. Now we discovered that they were island universes unto themselves. So this is the Andromeda galaxy, and it's actually moving towards us. How do we know that? It's blue shifted, right? So what we have found out also, and this is Edwin in the 200-inch telescope at Palomar, the Hale telescope at Palomar, which at the time was the largest telescope in existence. Huge telescope, a telescope so big you ride in it to take observations, because he's in the observer's cage there, right at the prime focus of the telescope. So here's another picture. This is absolutely my favorite telescope because I actually got a chance to go visit it and touch it and see it in real life. So this monster telescope, to give you an idea of the scale, this is me and a friend of mine when we went down to California to see it. This is us in front of that telescope. So gives you an idea of the scale of how huge it is. These days, it's not a big telescope in the greater scheme of things, but back then it was huge. And what it got used for is to extend out our view of how large the universe is. And we know, first of all, if you look at this little circle in the middle, we could see parallax, right? So we could look out at the stars and see that they moved, and we could determine their distance just based on geometry, basically. And once we saw Cepheid variables, we could tell in our galaxy how far things away were. And we could calibrate that a little bit because we could see Cepheid variables that we had parallax measurements for and compare the two measurements and see how far away they were. So what we discovered in other galaxies was Cepheid variables that enabled us to actually determine the distance. And then we discovered something else. We discovered something that was sort of similar. You know those giant stars that I was telling you about and the small stars? Well, if you put a big star next to a small star, the small star can eat away at the gas from the big star. And it eats away and eats away and eats away until it's so full it explodes. And it's called a type 1a supernova. Type 1a supernovas, kind of similar to Cepheid variables, we can actually tell based on what, the brightest that they get bright to a certain magnitude that we know, right? So once again, we have the great absolute magnitude, the actual brightness of the star, and we know its magnitude that we observe, and we can tell the difference, and we can see how far away it is. So type 1a supernovas extended our reach out even further. But what that also allowed us to do, and this is something that Edwin Hubble discovered, is if you take the spectrum of these stars and galaxies, you'll discover that the further away they are, the greater the redshift they have. In other words, they're all moving away from us. And that was the discovery that prompted people to create the Big Bang model of cosmology. If all of the galaxies that are really far away from us are moving away from us at a greater and greater rates, depending how far away they are, then obviously they were all at one single point at some point. There was a huge explosion, and now they're all flying away from us, right? So the last measure of distance that we have, which can detect stars or galaxies at the edge of the observable universe, is right back to what we talked about near the beginning, redshifts, right? Shifts based on Doppler. And I think that's enough for tonight. That's going from the really small scale to the really big scale. The last thing I wanted to say is try to protect our nighttime skies. We're starting to see a lot of lighting being put into Winnipeg, particularly, that look a little bit like this. This is actually a picture of some lights that were put in near my neighborhood, and they're very wasteful of energy, and they shine directly up in the sky, and they're destroying our beautiful nighttime skies. Whereas before, when we took a picture of the sky, for example, the constellation of Orion, we saw what we see on the left-hand side. Now with all these lights that have been put in, we see what's on the right-hand side, and it's destroying our nighttime skies. So if somebody ever asks you, sends you a survey, for example, asking you if they should put brighter lights in, say no. Thank you very much. Any questions?
Thank you, Gord. Let's see if anybody has any questions. There's nothing at the moment. So maybe what I'll do is I'll just finish up and see if any questions come up in the meantime. But I'd like to thank you very much for joining us today. We appreciate you taking the time to share with us your knowledge. And if anyone at home would like to enjoy going out and enjoying the stars, especially Gord talking about dark skies, we encourage you to head out to your local provincial park or even your backyard with a pair of binoculars or a telescope, because winter is a great time to go star watching. It gets so dark so fast, leaving more time for you guys to view the stars above. You can also download stargazing apps on your smartphone or a tablet like Skyview, Stellarium, or Starwalk. But just remember, when you do visit our parks, follow the COVID-19 public health orders, don't gather in groups, and practice the fundamentals of physical distancing and wearing a mask. So be sure to sign up for any other webinars, online events from Manitoba Parks. The next one is all about living with wildlife next Saturday at 6:30 p.m. Details and registration info is available on our Manitoba Parks website or our Facebook page. So at manitobaparks.com. So take care and stay safe at home. And let's just see if we have any comments. Well, we have, thanks, Gord, great presentation. We have a lot of thank you, awesome presentation. Thank you for hosting. And yes, there is a recording of this that will be available on the Manitoba Parks YouTube site. So you can go there. And everyone is basically just saying, thank you so much, Gord. So it looks like we don't have any comments or questions at this time. So if anyone does have any questions that pop up afterwards, to send an email to Manitoba Parks, we can get back to you and put you in contact with Gord.
And one last thing, my wife, of course, has a much better memory than me, and she reminded me that the play I was talking about with Henrietta Leavitt in it is called Silent Sky. It's a great play, so go see Silent Sky if you can.
Fabulous. I'm going to put that on the list. Thank you, Gord, so much for coming tonight. This has been wonderful. Bye, everyone. Have a great day or night.